Welcome to episode 15 of my calculus series. Today, we're diving into higher order derivatives. Ever wondered what happens when you take the derivative of a derivative and then keep going? By the end of this episode, you'll not only know how, it'll start to feel easy. But before we get into it, if you're enjoying these episodes, a like, follow on TikTok, or subscribe on YouTube would really help me keep making more lessons like this. Alright, let's get started. What are higher order derivatives? If a function f of x is differentiable, we can take its derivative, that's f prime of x. If f prime is also differentiable, we can take the second derivative, denoted f double prime of x, or d squared f over dx squared. This process continues. First derivative, f prime of x. Second derivative, f double prime of x. Third derivative, f triple prime of x. Nth derivative, f to the power of n in parentheses of x. Notation and interpretation. Let's look at some common notations. F double prime of x equals d squared f over dx squared f to the n of x equals d to the n f over dx to the n. In physics, derivatives show up like this. Position becomes velocity, then acceleration, then jerk. Interpretation. Higher derivatives can tell us the acceleration or how fast a rate is changing, the curvature of a graph, the concavity and behavior of a function. Implicit differentiation and higher derivatives. Sometimes we work with equations not solved for y. In those cases, we use implicit differentiation, and we can apply it multiple times. For example, we can find dy over dx, then d squared y over dx squared, and beyond. Examples. Basic second derivatives. Let's find the second derivative of f of x equals x cubed minus 6x squared plus 4x. Step 1. The first derivative is 3x squared minus 12x plus 4. Step 2. The second derivative is 6x minus 12. Next example. Find y double prime if y equals e to the 2x. The first derivative is 2e to the 2x. The second derivative is 4e to the 2x. Using the product rule, let's differentiate f of x equals x squared times natural log of x. Step 1. The first derivative is 2x times ln x plus x. Step 2. The second derivative is 2 ln x plus 2, plus 1, which simplifies to 2 ln x plus 3. Chain rule and higher derivatives. Example. Find y double prime if y equals sine of 3x. The first derivative is 3 cosine of 3x. The second derivative is negative 9 sine of 3x. Next example. Find the third derivative of y equals natural log of quantity x squared plus 1. Step 1. The first derivative is 2x over x squared plus 1. Step 2. The second derivative simplifies to 2 minus 2x squared over quantity x squared plus 1 squared. Step 3. The third derivative is a bit long, but it follows from the quotient rule and product rule. You'll see it fully expanded on screen. Implicit higher derivatives. Let's look at a classic circle equation. X squared plus y squared equals 25. Find the second derivative of y with respect to x. Step 1. Differentiate both sides. 2x plus 2y times dy over dx equals 0. That gives dy dx equals negative x over y. Step 2. Differentiate again using the quotient rule. We get the second derivative of y equals negative quantity y squared plus x squared, all over y cubed. Trigonometric example. Find the third derivative of y equals cosine x. The first derivative is negative sine x. The second derivative is negative cosine x. The third derivative is sine x. Summary. Here's what we learned in this episode. Higher order derivatives are just repeated derivatives. Notation includes f to the n of x, or d to the nf over dx to the n. The second derivative tells us about concavity. Third and higher derivatives show more nuanced behavior in the graph. And that wraps up today's episode. If this helped you out, don't forget to like, follow, or subscribe for more lessons. Thanks for watching, and see you in the next one.